While we looked at the uniform distribution to start our topic of continuous distributions, let's look at the normal distribution, which is probably the most recognized and granddaddy of all distributions. Almost every student learns this concept of the bell curve because it's something that they look at for their average. It is a very distinct and symmetric curve, but the properties around this distribution are very important across all areas of business and science. Let's look at a little history of this. The first person to derive the formula was Abraham de Moivre, a French mathematician who lived in England. His work focused on solving problems of chance, and he was looking for an easier way to compute probabilities, which ended up leading to his work on the normal distribution. Carl Gauss is credited with additional work leading to the concept of the normal distribution law, and also contributing to this work was Pierre-Simon Laplace, who appeared to finalize the work in 1810 with the work formalizing the central limit theorem around this and establishing the theoretical importance of the normal distribution. So these are the three people who are probably most influential in creating this normal distribution and providing you with the information on what you need to know about your grades and the average. The reason this is important is because you may hear the term Gaussian. Gaussian is going to refer to a normal distribution. That's who it's named after. Mathematically, the formula for the normal distribution looks a little complicated, but it has a few key components here, and many of these we'll recognize. So the first one, if we look to the left of the E, we have 1 over sigma times the square root of 2 pi. Well, sigma is our standard deviation, and pi we know as 3.14. Then we have the letter E. That's our natural constant of 2.71828. We see that in finance and all the sciences for decay, growth rates, and so forth. And then again, we're going to see this in the top part of the exponent of E. We're going to have x minus mu divided by sigma. Again, we know x is an individual number. Mu is our mean. Sigma is the standard deviation. We square that, and that gets multiplied by the front side, which is negative 1/2. Not going to be required to memorize this formula, but I put this here to show you that you understand the pieces, and it is possible to use this to compute the actual probability for anything that has a normal distribution. The parameters of the formula are variables that will change based on the data. So in this case, the mean and the standard deviation. These two parameters can be referred to as the location and shape. Location because that mean is telling us where it sits, where that center of mass is, and the shape because the standard deviation or the variance tells us the spread around that mean. Is it narrow? Is it further out? And so forth. The mean provides the highest and central point of the curve, and as we said, was the location. And the standard deviation does provide the shape because a larger standard deviation means the spread of the data will be wider, while a smaller standard deviation would show a much more narrower peak in the middle. Another key point is that the normal distribution is extended infinitely in both directions, and therefore it is called unbounded. It will go off to the left at infinity, off to the right at infinity. But it's important to know that the probabilities of those further and further out get much, 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 much smaller. So they'll go from 0.01 to 0.001 to 0.0001 and so forth. And it's going to basically be 0 at that point. The probability in the tails, that is the part that is extended infinitely in both directions, is where outliers might lie. And so the tails become important for analysis later on to understand that this is the probability of these out-of-bounds numbers. Another important aspect of the normal distribution is that it is symmetric, meaning it has a mirror image around the vertical line, specifically around the mean. This shows that the mean here represents a point at which 50% is to the left and 50% is to the right. By definition, the mean and the median are therefore equivalent in a normal distribution, and it is the specific reason why in practice the average provides a sense of the middle. So it only provides that because people assume that it follows, or whatever data they're looking at follows a bell curve. The term skewness refers to a shift or leaning of the curve. Since the normal distribution is symmetric, there is no skewness, and thus the skewness value for a normal distribution is 0. We said earlier that the standard deviation is used to determine whether the tails were very narrow or slightly larger. The chart here on the right shows 3 normal distributions with the exact same mean of 0. but 3 different standard deviations. Standard deviation of 1, 3, and 5. The red line has a very narrow middle with a standard deviation of 1, and very flat tails. Notice how as the standard deviation begins to increase, so the tails become wider at the same values. It is in these regions that we have these extreme values, and thus the wider the tails, the more likely the propensity of these outliers will occur.